The first method we're going to look at in terms of solving ordinary differential equation is a method called Euler's method, and we learned Euler's method in Eng 1060, so I'm not going to spend a lot of time going through this. So Euler's method is the simplest way of finding the solution of the ODE dy dt is equal to some function of t and y. And in actual fact, Euler's method, if you like, is the building block on which all other methods are based. So you must understand Euler's method to understand any of the others. We can derive Euler's method in several different ways. So we're going to look at one way of doing it here, and I recommend that you understand how this works because it might be a question I would ask on an exam. So if we have the black line there, and that's the solution to our ODE, we don't actually know what it is, but we do know that we've got the solution at time is equal to ti, and that's given by yi. So nomenclature-wise, yi is just equal to our solution at time ti. What we're trying to find now is, what is the solution at some other time? Let's say it's ti plus 1, which is given by ti plus h. So that distance between ti and ti plus 1 is given by a distance h. And we're trying to find what the value of the solution is at this time. So let's consider the Taylor series of the solution at t is equal to ti plus h, or equivalently ti plus 1. So y of ti plus h is equal to y of ti plus h dy dt, evaluated at ti, plus h squared on 2 d squared y dt squared, evaluated at ti, plus higher order terms. That's the standard Taylor series. You absolutely need to know that off by heart. Now if we truncate this expression at first order, in other words, we ignore that term and all of the higher order terms, we can then see that y of ti plus h is equal to y at ti plus h times dy dt. But we also know from our original ordinary differential equation that dy dt is equal to f of ty. So if we substitute this in for this, we get y of ti plus h is equal to y of ti plus h times f of yi ti. Of course, there's going to be some error terms here as well. This equation here is Euler's method, and I recommend that you commit that to memory. Another way of looking at this is to look graphically at what is happening here. So imagine we have the point tiyi, and we can calculate the slope of the solution at that point. Of course we can from the function that we're given in the original ODE. So we have the solution at the red point here. We can calculate the solution at that point. The slope of that solution is just given by that blue line there, and it's exactly given by that function of ti and yi that we have on the right hand side of the ODE. With Euler's method, what we do is we're assuming that the slope of the solution is constant over the interval h. In other words, the solution slope doesn't change. Now we can see from our black line here, which is the actual solution, that this is not true. However, it's an approximation, and as h becomes smaller, it becomes a better and better approximation. So what we're now trying to do is we're trying to find how much our solution gets bigger as we move across this interval h, and that number is given by this value here, delta y. So we need to try and calculate how big this increment is in the y direction. That will then give us our estimate for yi plus 1. Well, we know the slope of that triangle is delta y divided by h. That's just the rise over the run. We also know that that's got to be equal to our function value at the start point here, because that's how we've defined it. Therefore, delta y, the change in our solution, is given by h times the function value evaluated at the beginning point. So if yi equals yi plus delta y, which it is by definition, then yi plus 1 is equal to yi plus h times the function value at the beginning of the slope. And again, we've derived Euler's method. So obviously from this figure there's an error, and that's given by that little green increment here. It's the difference between where we have found the solution and what the actual solution is on the black line down here. From Taylor series, if we go back to the Taylor series, we can see that the leading order error term is that term there. So it's proportional to the second derivative of y, and it also scales like the spacing squared. So, in summary, Euler's method uses the slope, dy dt, at the beginning of the interval to calculate a new estimate of y at the end of the interval. That's ti plus 1. We're assuming that the initial slope is a good approximation for the entire interval, but we know that that's not really true. We're going to see later that there are better ways to approximate the slope, but that will come in subsequent videos. So far we've only done one step of Euler's method. How do we solve for multiple steps? Well, let's start with our initial condition t0, y0, and use Euler's method with I is equal to 0. So what we're going to do is, this is the Euler's method up the top here, we're going to set I is equal to 0, and so we're going to calculate y of t0 plus h, which is just simply equal to y of t1, and we're just going to call that y1. So all of these three things here mean exactly the same thing. And based on Euler's method, that is the equation up the top here, that's equal to y of t0 plus h times f of t0 y0. So we go from this point and we jump up to that point there. Now that point there is not on the black line because there's an error involved. Next, we use Euler's method with I is equal to 1. And that then gives us y of ti plus h, which is y of t2, which is just equal to y2, is equal to y of t1 plus h times the function evaluated at t1, y1. And that takes us to that next red point. We then use Euler's method with I is equal to 2, and so on. So we loop through the number of steps that we want to take, doing this kind of thing every time. So we saw previously from the Taylor series that there's an error in Euler's method, and the error scales like this this leading order term in the Taylor series expansion. It's given by approximately h squared on 2 times d squared y dt squared evaluated at the beginning of the interval. That's the magnitude of the error. So what's the significance of the fact that the error scales like this? Well, clearly, if we take a smaller step size, h, the error also decreases. So, if we halve h, replace h here by h on 2, and we see that for a half step size we get 1/4 the error. That's for a single step of Euler's method. So that's what we've got to begin with. If we take a smaller step size, we can quite clearly see that the error here is going to be smaller than the error in the other case, because we haven't gone so far from the initial point, and we haven't had such a chance to get or accumulate such a big error. But if you halve the step size, to get to the end point you need to take twice as many steps. So what does this do to the total error? Half the step size, each step size is 4 times more accurate, but twice as many steps. It's not entirely clear how that's going to affect the error. So in order to estimate this, let's consider going from t is equal to a to t is equal to b and taking n steps. Let's assume the worst case scenario where each step introduces an error that's given by h squared on 2 times the second derivative of y on dt squared. Then the total error is just the sum of each of the individual errors as we go across each of these intervals. So the sum total of errors is equal to the sum of epsilon i's. I is equal to 1 to n, where there's n intervals. That's just equal to the sum of these error terms there, because that's how we've defined the error. And that's just equal to h squared on 2. We can pull the h squared on 2 out, multiplied by the sum of the second derivative estimates in each of the intervals. So let's just write that error term up the top here again. We can make an estimate of the average value of the second derivative over this interval a to b. So y double dashed bar, that just means the average value of the second derivative, is approximately equal to the sum of the individual second derivative estimates at each of the intervals divided by the number of intervals that we've got. So we're just summing up the estimates and dividing by the number of estimates to give us an estimate of the average error. Sorry, the average second derivative. Now, by definition, our step size h is equal to b minus a divided by the number of intervals. And so then it's very easy to show that 1 on n is simply equal to h divided by b minus a. So we can replace the 1 on n here with h divided by b minus a to give us an estimate of the average second derivative given by that expression there, h on b minus a times the sum. Or, just swapping things over a little bit, that the sum of d squared y dt squared is equal to b minus a divided by h times the average value of the second derivative. So we can put this into our expression for the total error, as we do down here, and show that the total error is approximately equal to h times b minus a on 2 times the average value of the second derivative. So what this says a few different things. Whatever the step size is, the error is going to scale linearly with the step size h. B minus a, provided those two things are fixed, they're not going to change the way in which the error scales, and the average value of the second derivative over a particular interval isn't really going to change either. So the error only scales with the step size h. So if we double n, in other words halve h, we can replace h by h on 2, so replace that h there with h on 2, and we can see that the error now scales like h on 4 times b minus a times the second derivative. So in other words, the error is halved when we halve h. So that's not really so great. We'd like to be able to improve our error more than linearly with the mesh spacing. So this highlights some important concepts of error in our ODE solution, and these are going to come up time and time again, so I'll introduce them here but raise them again later. There is something called the local truncation error, and the local truncation error arises from the application of Euler's method over a single step. And this is a consequence of the method only being approximate. In other words, we haven't included the higher order terms in the Taylor series expansion. There is a global or propagated truncation error. This arises from the accumulation of the local errors plus how these errors are propagated from step to step. So the global and the local errors can be quite different. And we saw for Euler's method, the local error was order h squared, but the global error was order h. And of course, there is always a round-off error that's caused by limited significant figures inside the computer. We can't avoid that one.